All right, let's get right into it. We're about to explore an experiment that didn't just tweak our understanding of science, it completely tore up the textbook and rewrote it from scratch. This is the incredible story of how we discovered the very heart of the atom. So get this. That's how Ernest Rutherford, the guy running the show, described his own results. Just let that sink in for a moment. You shoot a cannonball at what should be the flimsiest material imaginable, and it ricochets back and hits you. The shock, the sheer impossibility of it is what we're talking about today. And really, that's the big question, isn't it? What on earth could be hiding inside an atom that's strong enough to smack a high-speed particle right back where it came from? To get why this was such a jaw-dropping moment, you first have to understand what everyone thought an atom looked like before this all went down. So let's hop in the time machine and rewind. Before this experiment, the scientific world had a totally different idea about the atom, and honestly, it had a pretty tasty-sounding name. It was called the plum pudding model. Think of it like a blueberry muffin, or, well, a plum pudding. The idea from Thomson was that the atom was this big, spongy, positively charged cake, and scattered all through it, like blueberries, were these tiny negative electrons he'd discovered. So the most important takeaway from this model is that there was nothing hard or dense anywhere inside. All the mass and all the positive charge were just kind of spread out evenly, like a mist. There was absolutely no concept of a solid core, no nucleus. And this is the theory that Rutherford decided to put to the test. And so, Rutherford and his team, Hans Geiger and Ernest Marsden, came up with this brilliantly simple experiment to see what was really going on inside this pudding. The plan was basic, really. Let's just shoot stuff at it and see what happens. Okay, so here's the setup. First, you need your bullets. They used a radioactive source to shoot out a stream of tiny, positively charged things called alpha particles. These are your microscopic cannonballs. Step 2, you need a target. They aimed that beam at a ridiculously thin sheet of gold foil. And finally, step 3, you need to see where the bullets go. So they wrapped a detector screen around the whole thing that would make a tiny flash of light anytime an alpha particle hit it. Now you might be wondering, why gold? Well, this was just a genius move. Gold is so incredibly soft and malleable that you can pound it down into sheets that are just a few thousand atoms thick. And that was absolutely key because it meant the alpha particles would probably only have to pass through 1 or 2 atoms, keeping the results nice and clean. So, what did they expect to see? Well, based on that plum pudding model, the answer was not much. Firing a heavy, fast particle at a fluffy, misty atom should be like firing a cannonball through a cloud. They figured almost all the particles would just sail straight through, maybe getting nudged just a tiny, tiny bit. But that is not what they saw, not even close. What they found, after hours and hours spent in a dark lab counting those little flashes of light, was about to blow the world of physics wide open. All right, so observation number 1 was pretty much exactly what they expected. The huge majority of those alpha particles just zipped right through the gold foil like it wasn't even there. Okay, so far so good. That seems to support the idea that atoms are mostly empty space. But then things got a little weird. They noticed that a small number of the particles didn't go straight through. They were actually deflected, veering off course by a few degrees. Okay, that's interesting. That hints that there's something in there with enough of a positive charge to push their positive little cannonballs away. Still, not the main event. The real stunner, the number that changed everything, was this one. Roughly 1 out of every 20,000 particles didn't just get nudged. It did something that was supposed to be impossible. It bounced back. Some were deflected at massive angles, and a few flew almost straight back at the source. This was the cannonball hitting the tissue paper. The plum pudding model had zero, and I mean zero, explanation for how this could ever happen. When you see something that impossible, you can't just tweak the old theory. You have to throw it out and start over. Rutherford realized the only way to explain this was to completely rethink the atom from the ground up. Suddenly, every weird observation became a clue. Most particles flew straight through. That's because the atom is almost entirely empty space. A few got deflected. That's because the atom's positive charge isn't some diffuse cloud. It's all packed together in one spot. And that crazy 1 in 20,000 that bounced back, that was the smoking gun. It meant that they'd scored a direct hit on a tiny, incredibly dense, and massively positive center. And this just shows you the night and day difference. On the left, you have the old plum pudding model, this soft, squishy ball. And on the right, you have Rutherford's new nuclear model. In this picture, almost all the atom's mass and all its positive charge is crushed down into an impossibly small point called the nucleus, with the electrons orbiting far away in a vast sea of emptiness. The cannonball wasn't bouncing off tissue paper, it was bouncing off a microscopic anvil hidden inside. This discovery wasn't just some minor correction. It was like kicking open a door to a hidden universe. It was the birth of an entirely new field of science, nuclear physics. And look at the domino effect. Just 2 years later, Niels Bohr uses this new nuclear model to figure out how electrons orbit. Less than 20 years after that, the neutron is discovered, finally giving us the complete picture of the nucleus. Literally all of modern nuclear physics stands on the shoulders of this one single experiment. And don't think for a second this is just old history. The basic idea, shooting particles at stuff to see what's inside, is at the heart of technologies we use every single day. Huge particle accelerators, how we analyze materials to build better computer chips, even the very foundations of nuclear energy research, you can draw a straight line from all of it right back to Rutherford shooting alpha particles at that little sheet of gold foil. Which kind of leaves you with this one big, fascinating question. Rutherford's story is the ultimate reminder that the biggest revolutions in science don't come from proving what we already think is true. They come from finding something that makes absolutely no sense. So we have to wonder, what impossible result, glowing on a computer screen in some lab right now, is our generation's cannonball bouncing off tissue paper?